reads, a steam pipe is 120 millimeters outside diameter and 100 millimeters in the diameter. This pipe has a length of 30 meters and passes through a wall against both ends where it is rigidly constrained. Steam at 200 degrees Celsius is suddenly released into the pipe. The initial temperature of the pipe is 15 degrees C, and the coefficient of linear expansion measures at 15 times 10 to the power minus 6 per centigrade. Assuming that the Young's modulus of the material used in manufacturing the steam pipe is at 200 GPa, we've been tasked to calculate the following. We need to calculate the thermal stress produced due to the steam, and also the force exerted by the pipe against the wall. And we're going to look at this from two perspectives. So these are the expected results. So in terms of the thermal stress, we are expected to get a value of 555 MPa. And in terms of the force exerted by the pipe against the wall, we're looking at 1.92 meganewtons. Okay?
Now I did say something about, okay, what if there was a measure of constriction and we were to calculate what would be the corresponding radial force? So we can figure out how to go about calculating the radial force, and we can probably work out what the resultant force would be, so that that can be factored into the design of the pipe. Because again, anything can happen, right? So let's look at worst case situations. So how do we go about working this out? So there are some other variables that need to be introduced, and these variables I will elaborate further down the line when we start looking at two-dimensional stress systems. Okay, once we've completed our series on one-dimensional stress systems. So this is what I'm going to do. I'm going to first work out what the longitudinal strain is. So let's say that the longitudinal strain let's call that epsilon x, right? So that will be equal to alpha times the temperature differential. Okay, let's call that equation 2. Okay, so this will be equal to 15 times 10 to the power minus 6 times the temperature differential. So that will be 200 minus 15. That is 185. Alright. Now let's not forget that the units will come out, thus leaving strain dimensionless. So let's see. 15 10 to the power minus 6 times 185. Alright. So the strain, longitudinal strain is equal to 2.775 times 10 to the power minus 3. Okay. So I'm now going to introduce another variable, okay, another property that will show what the relationship is between the longitudinal stress and the lateral stress. Alright? And this is what we call the Poisson ratio. Okay, so the Poisson ratio determines that. So let's introduce what's called the Poisson ratio. So Poisson's ratio. So that characterized by nu. So that is nu. And that is equal to the ratio of the lateral strain to that of the longitudinal strain. Okay, so let's call that equation 3. Alright. Now, normally, if you have a longitudinal stress taking place, alright, so let's assume that the tube is stretching. We have a situation whereby the tube is also reducing in its cross-sectional area. So we can look at it from that context. So there are two situations that we can use here to review what's going on in terms of the two. Right? So we can either do that, Or if we're assuming that there is going to be some measure of expansion, then what we can do is we can assume, right, that in this context, the lateral stress will be greater than the longitudinal strain. Sorry, the longitudinal strain. So the lateral strain will be larger than the longitudinal strain. Thus, you're going to have a situation whereby the Poisson ratio is actually divided. Okay, so we can look at that in that context. So in this context, I'm more or less looking at the extreme. Okay, but I'm going to be looking at two situations regarding that. So situation one. So assuming, okay, so we're going to assume that the longitudinal strain is going to affect aerial reduction in Y. So therefore, epsilon x is going to be greater than epsilon y. So if that's the case, mu is going to be equal to epsilon y for epsilon x. Okay. So therefore, epsilon y is going to be equal to nu times epsilon x. Okay. So in this context, right? In this context, this is the assumption that we're going to make to look at what would be that lateral force, right? And we're also going to look at situation 2. So if we're going to assume that based on constriction, possible constriction in the pipe, that the lateral strain is going to be larger than the longitudinal strain. So assume that the constrictions is going to cause sigma y to be greater than sig epsilon x, so that's not sigma, that's epsilon. Then we're going to have a situation whereby epsilon y is going to be equal to epsilon x divided by mu. So this defines extreme situation with respect to expansion, okay, to the diameter of the pipe due to what? Constriction that's going to cause internalized pressure. Okay, so we can make that simple assumption here. Alright, so let's work through situation 1 and compare the force. So situation 1, where epsilon x is greater than epsilon y. So we stated that epsilon y is going to be approximately equal to nu times epsilon x. Nu here, we're going to assume that to be about 0.3, which tends to be nominal in a way. Particularly if we're assuming that deformation in the material is elastic. Okay, so we're assuming that the material is not plastically deforming. Okay, so we're going to make that assumption. So that will be 0.3 times 2.775 times 10 to the power minus 3. So again, no units. So multiply that by 0.3 and that would give approximately 8.325 times 10 to the power minus 4. So this is essentially the strain that's being experienced by our pipe. So if this is the case, then we can calculate the corresponding thermal stress, okay, with respect to y. So since strain is equal to stress divided by E, then we can assume that the thermal stress in Y, so the Y plane, the Y axis, so let's call that sigma Y for the purposes of what we're doing, equal to epsilon Y times E. Okay. So this becomes 8.325 times 10 to the power minus 4 times 200 times 10 to the power of 9. So let's bring our calculator. So times 200 times 10 to the power of 9, and that gives 166.5 times 10 to the power of 6 PA. So that is 166.5 MPa. Okay. So longitudinally, we got a value of what? 555 MPa. So failure is likely to occur longitudinally in the context of the question that we've been provided. So the stress is quite minimal in that regard. So if we're going to calculate the force, so we're going to look at the lateral force, so let's call that, so the lateral force, let's call that Fy, that's going to be equal to sigma Y times A. Okay, so that's basically the lateral stress, the lateral force that's going to possibly cause some measure of shearing. Okay, and that's the force that's more or less being that's causing radial compression in the wall or against the wall. Right. So we've already calculated the area of the pipe. So we calculated the area. Did we calculate the area? No, I don't think so. Yeah, we did. We calculated the area. Alright, so the area previously was what? 3.4558 times 10 to the power minus 3 meters squared. Alright. So this becomes 166.5 times 10 to the power to the 6 by 3.4558 times 10 to the power minus 3. And all that should give our units in newtons. So times 3.4558 times 10 to the power minus 3, and that would give 575,390.7 newtons, which is approximately, if you're going to do it the same on the same basis in terms of meganewtons, and that would be 0.575 meganewtons. Okay. Alright, so the force is literally less in comparison to the longitudinal lateral force. So let's look at worst case from the situation whereby, so let's look at situation 2. And I think in terms of designing for reliability, it's always best to factor a situation whereby there is possible constriction in the pipe. Is that going to cause the pipe to burst radially? So let's look at worst case. Okay. So worst case, we stated that epsilon Y will be equal to epsilon X divided by mu. Right? So this will be equal to 2.775 times 10 to the power minus 3 divided by 0.3. Okay. And that would give 2.775 times 10 to the power minus 3 divided by 0.3. So this gives 9.25 times 10 to the power minus 3. And we followed the same methodology as previously. So therefore, the thermal stress let's call that sigma y will be equal to epsilon y times the Young's modulus. Okay. So sigma y is equal to 9.25 times 10 to the power minus 3 times 200 times 10 to the power of 9. Okay. So our units would be in PA. If you want to have your units in Newton per meter squared, is up to you. There we go. Thought my calculator was dead. So 9.25 times minus 3 times 200 times 9, and that would be equal to, so let's see, we've got 1, 2, right, so that is approximately 185 times, how many zeros, 10 to the power of 7 PA, so that is quite large. That is 1.85 GPA, or if you want to go with 1,850 MPa. So we can look at that in comparison to what we got previously. So if you're comparing this situation whereby if there's going to be that possible constriction within the pipe, then we're looking at the stresses superseding that of the longitudinal stress. Okay. So therefore, if you're going to look at that load that's likely to be subjected to the wall laterally, then the lateral force so let's call that Fy. That'll be equal to sigma y times the sectional area. So it's more or less similar methodology to what we used previously. So this becomes 1850 times 10 to the power 6 times the sectional area, which is 3.455 8 times 10 to the power minus 3. That, so 3.4558 times 10 to the power minus 3, and that would give 639.3230 newtons. Okay, so this is approximately 6.39 mega newtons. Okay, so we've got a situation whereby if we look at possible constriction within the pipe, then the lateral force is going to be almost 4 times that of the longitudinal force against the wall. Okay, so if you want to, you can use the measure of the forces to work out what the resultant force is likely to be. Alright, so if you want to have a go at that, let's call the resultant force Fr, and that's going to be equal to the vector sum of Fx squared plus Fy squared. You can use this information to probably work out the direction. So I'll let you guys have a go doing this bit. And there you have it.
So let's look at a situation where some form of lateral force is being generated, if we're assuming that there's that possibility of the pipe being constrained, and that's going to cause excessive pressure buildup. Now, normally we could look at using the appropriate formula when we're looking at stresses in cylinders, calculating the hoop stress and the radial stress. But to keep things simple, what we're going to do is we're going to introduce what's called the Poisson ratio, and I'm going to talk about that in a later series down the line. So the Poisson ratio is basically the ratio of the lateral stress to the longitudinal, the lateral strain to the longitudinal strain. So that's essentially what the Poisson ratio is. So for this given material, the Poisson ratio, we're more or less going to assume it to be 0.3. Now, since we're assuming that the pipe is more or less expanding due to maybe constrictions in the pipe, we're going to assume that in this context, the Poisson ratio, the lateral stress, will be larger than the longitudinal strain. Okay, so to calculate the lateral strain, that will be equal to alpha times delta T divided by the Poisson ratio, if we're assuming that the diameter of the steam pipe is expanded. So we put in the known values and we get a strain of 9.25 times 10 to the power minus 3. So to calculate the stress, we know that stress divided by strain is equal to E. Thus, stress is equal to epsilon, which is the strain, times E. So if we put in known values, we get the lateral stress to be equal to 1,850 or 1,850 MPa. So by knowing that, we can then calculate what the lateral load is. So that will be F subscript Y, and that will be equal to the lateral stress times the cross-sectional area. So we calculated this lateral stress to be 1,850 times 10 to the power 6 times the cross-sectional area, which measured at 3.4558 times 10 to the power minus 3, and that gives a measured lateral force of 6.39 meganewton. So if we were to work out the resultant force, or the vector sum of the two forces, we get approximately 6.675 meganewtons. And there we have it. Alright folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.